So today we are going to discuss the third topic of Unit 1, that is the vapor-liquid equilibrium. So the first lecture regarding the vapor-liquid equilibrium that tells about the some important factors of the vapor-liquid equilibrium. Uh, so before going to the vapor-liquid equilibrium, now let us look a brief about the phase rule, as it is very important for the equilibrium conditions. So normally the phase rule is related with the variables of the system in the thermodynamic equilibrium. So that is an important thing. That's why we are basically we have to know about the phase rule, and there are very simple equation that for the phase rule, where f is equal to c minus p plus 2, and where the meaning of these terms is f is the number of degree of freedom that we need to find out with the help of c and p. What is the c? C is the number of chemical components, that's a component. P is the number of phases. So putting all these values, we can find out the value of f, that is the number of degree of freedom. Let us take an example. For example, if we have only one component, uh, so number of component is 1, c is 1, and the phase is also 1, simple, a liquid phase. So what will be the degree of freedom? So c minus p plus 2, it gives the value is 2. So now there are two freedoms we have. F is equal to 2. We means we have a two independent variable to handle it. We can change these two variables to fix the equilibrium conditions of the single phase and single component system. Normally the variables that is available is the two variables that is available is temperature and pressure. So this is the one aspect where the single component, single phase. Now let us take a simple example of triple point equilibrium points. Triple point is the point where all these three phases are come across together, means they are mixed together. So in the same case, number of component is 1 here, number of phase is 3 here. When vapor, liquid and gas, all these three phases are combined in the triple point. So what will be the degree of freedom if you put these values in this equation? So you will find that the degree of freedom value becomes 0. 0 means we have no freedom to fix the variables. So it means that there is no choice for changing that point, that triple point. So that's why the triple point that is at equilibrium is have no choice. So that means that the system is already fixed at a given temperature and pressure. So triple point temperature and pressure for each and every component is fixed. We cannot change it. There will be a single point. So similarly, we can go for the binary system also. So the phase rule is a very important to tell about number of equilibrium variables, that is the number of variables required for the equilibrium. So for the binary system, if you are going for the phase rule, so number of phases in the vapor liquid equilibrium, so there are two phases here. So one phase is vapor, one phase is liquid. Okay, number of components, because we have taken the binary system, means number of components is 2. Putting these two values in the c minus p plus 2, we will observe that the f value, that is the degree of freedom value, is 2. So we have a degree of freedom of 2. What are the different variables, independent variables? So we have a different variables. One variable is temperature, one variable is pressure, one variable is a liquid phase composition, and one variable is the vapor phase composition. So there are 4 different variables, and a number of independent variables total is 4, and we have only 2 variables that need to be fixed out, that is the freedom. So by fixing the 2 variables, like we can fix the pressure, we can fix the temperatures, then what happen, other variables automatically will be fixed out, means that liquid composition will be fixed out, vapor composition will be fixed out, if these two, pressure and temperature, will be fixed. So that is why sometimes what happen, this in our case, this pressure is fixed. Normally we do the VLE data, means vapor liquid equilibrium are carried out at a constant pressure. So one variable is fixed, only one freedom is left. So means if you fix the temperature, so automatically the composition in the liquid and vapor phase will be fixed. If you change the temperature, for example, if you fix the temperature T1, then the composition will be fixed. You take the second temperature T2, then again the new composition of liquid and vapor will be fixed out, that will be in an equilibrium. So that is the concept here. where normally in our cases normally we fix the pressure and we can change the temperature at every different at each temperature we can observe the composition of liquid and vapor, and that is fixed at that particular temperature. It means that at equilibrium we cannot change the composition of a liquid and vapor at that particular temperature. So now let us look about the terminologies that I'm going to use in the vapor liquid equilibrium. These are terminologies that are very common. So we should know about these things. For example, one terminology we are going to use is the bubble point temperature. So obviously it means that there is temperature. So bubble point temperature is defined as the temperature at which the first bubble of gas appears at a specific pressure, means at a constant specific pressure. What happen if there are mixture A and B is there, which are in the liquid phase? What happen if you provide the heat? The A and B both will be going try to move from the liquid to vapor phase, but the more volatile will be going into the vapor phase first. So temperature at which the first bubbles of the gas is formed, so that is known as the bubble point temperature. So the bubble point temperature, in other words, is the temperature when the first bubble of vapor is formed when the heating of a liquid consisting of two or more components are carried out. This is the same definitions in some other way. That is the bubble point temperatures. And what is the meaning of bubble point curve? Bubble point curve means locus of all the bubble point temperature at various compositions is called the bubble point curve. So this is also called as the saturated liquid curve. So bubble point curve or saturated liquid curve both have the same meaning, same thing, and it is nothing but the bubble point temperature. What it means, the bubble point temperature? There are different bubble point temperatures because we have a different composition in the liquid phase. For binary system we have a different composition. For example, one composition could be a 20% A and the remaining is 30%, 70% is B. Second composition we have 40% A and 60% B. So for these two compositions we have a different bubble point temperatures. So in this way we can have a different values of the bubble point temperatures. If you put all these values, these temperatures with compositions in the graph, we can develop the bubble point curve, and that is nothing but the saturated liquid curve. Then there is one more definition that is called a dew point temperature. That is the interesting thing for the mixture. It is defined as the temperature at the first drop of the vapor mixture begins to condense at a specific and constant pressure. Means this is the opposite of the bubble point temperature. In the bubble point, things are going from liquid phase to vapor phase. When it is just started from materials from liquid phase to vapor phase. But in the dew point, materials are going from vapor phase to liquid phase. The starting point of the materials that is going from vapor phase to liquid phase, that is called the dew point temperature. And again, the locus of all the dew point temperatures at various compositions is called the dew point curve, and the alternative name of that dew point curve is the saturated vapor curve. So that tells about the composition in the vapor phase. So this is the dew point. Both values are different. Dew point values are different from the bubble point values, but in the pure component these bubble and dew point both are same. For example, in the water, so what happened, water will be boiled at 100 degrees Celsius, means it changes the phase from the liquid phase to vapor phase at 100 degrees Celsius. And similarly, when everything is in the vapor phase, when all the water is in the vapor phase, then what happened if you condense it? So at 100 degrees Celsius it becomes in the liquid from vapor phase. So both the values, bubble point and dew point, both are same in the mixture in the pure component, but in the mixture it is different. Bubble point is always lower as compared to a dew point. Dew point temperature is always higher. Just for example, if suppose we have a and B, and what happened, A is 40% and B is remaining is 60%. This is A, and everything is in the we want to just vaporize it. So what happened, it will be vaporizes and bubble point will be observed. Say for example, bubble point is 70 degrees Celsius, and when we again supply the heat, the things will be vaporizes, and at certain temperature it will be completely vapor phase. So if you reverse back, if you condense it, what happened, you will observe that this 70 degree is the bubble point, but if you observe that at 80 degree this composition will be condensed out. So it means that the dew point is 80 degree and 70 degree is the bubble point. So always the dew point is higher for the same composition as compared to the dew point, as compared to the bubble point, sorry. Now the next one is a tie line. Tie line is also important things. It is a straight line at a specific constant temperature that join the saturated liquid curve to saturated vapor curve. So in the next slide I will give you the pictorial representation of all these things. So what is the significance of this tie line? Basically, tie line gives the equilibrium composition of vapor and liquid at a particular temperature, at a specific temperature. So that is the significance. So with the help of tie line, we can find out the different compositions at a specific temperature. The last point that is missing here, that we can draw infinite number of tie line in the any given diagram, in any given Valley diagram. So infinite tie line basically can be possible, and I can show you in the next slide. So now come to the vapor liquid equilibrium curve. So this is the curve. This is called a TXY diagram. So where y-axis is the temperature and x-axis is the composition in the liquid composition and vapor composition. This blue line is the liquid composition. This red line is the vapor compositions. Now let us one by one. So what I discuss, all these diagrams are developed at a constant pressure. And now see here, this is the saturated liquid or the bubble point curve. This one is the bubble point curve. Okay, so I have already explained what is the meaning of bubble point and bubble point curve. So this is the curve of locus of all the bubble point temperature, means this is the point at which the first bubble forms. For example, if suppose this is our composition 0.4, so you can see that at this composition the things will be vaporizes, means bubble point will be near about 90, 95, 97 and so on. And if the composition is 60%, A is 60%, you will see this one, this is near about 90 degrees Celsius. And if it is 100%, one means A is 100%. So this value, you know, this value is the boiling point of the 100% means pure A. So that is nothing but the boiling point of A. Similarly, if A is 0 means 100% B. So 100% B means the boiling point of B, and that is, for example, in our case 110 degrees Celsius. So these two ends are basically the pure B and pure A, and it tells about the boiling point. But between these two ends there will be a composition, and for each and every composition you will observe that there are two curves. One is the bubble point curve and the second is the dew point curve. So dew point curves is basically when the materials are coming from this vapor phase to liquid phase. So at that condition you will, for example, for the same 40%, this 0.4 is vapor phase, and when it is condenses, you see that this is the dew point. It comes around 100, maybe it is 102 degrees Celsius. So at the same composition, dew point is 102 degrees Celsius and bubble point is about 96 degrees Celsius. So that's why I told you that always the dew point is more as compared to the bubble point for the same composition. And the second, in between these two curves, these are basically the this is called the vapor liquid mixture region, VLE region. Vapor liquid mixtures are there here, and again below the saturated liquid curve means these positions, these are the positions where everything is in the liquid phase. So that is called the subcooled liquid section. All these below the saturated liquid curve, and above the saturated vapor, this is called the superheated vapor. This is the basically above the saturated vapor. That is called the above the saturated vapor is called the superheated vapor. So this is the different name of the different zones of the TXY diagram. And one more thing I have shown here is the same red color, so that creates a problem. This is a tie line. You know, tie line means at a fixed temperature what is the composition of vapor phase, and this is the composition of vapor phase, and this is the composition of liquid phase at that particular temperature. This is called the tie line. This is all about the vapor liquid equilibrium curve. These are the different types of the basically zones and different important things that are shown here. And this is the second diagram, XY diagram. So it's this is the working diagram. Basically we have to use more and more this XY diagram as compared to TXY diagram. In the XY diagram only there are two lines are there. So at constant pressure it is also generated. This is y is equal to x line, means 45 line, and this is the equilibrium line where the y is a function of x, that is developed by the txy1. So I hope you can understand all these things. Now let us take a simple example, what is happening, how the composition changes. For example, if suppose we have a mixture of 40% A and the remaining is 60%, and this is the temperature. This is the position. If I say 40% A at 70 degrees Celsius, we can say that it is a subcooled. Means the material is now in the subcooled position. We supply the heat. What happen if I supply the heat? So what happened, the temperature will increase, but there will be no change in the phase. Temperature will increase until and unless it reaches up to this point, means this one. At this point what happened, the first, when you supply the heat, then the first vapor will be formed, that is called the bubble point temperature. So we can find that the bubble point temperature, it comes around 95-96 degrees Celsius, for example, in this case. So what happened when the first vapor is formed, what will be the composition of that vapor? That vapor always will be in equilibrium with this liquid, and the composition of that vapor will be at that temperature. You can find out, this is the composition you can find out. So means the composition of A in the vapor phase is about 60, and it comes be 63 and 64% A in the vapor phase. So in the liquid it is 40%, but in the vapor it is 63%. So it means that A is more in the vapor phase. And again, if you supply the heat, what happens? So if you supply the heat, more and more vapors will be formed, and the situation will be a vapor and liquid mixture. So if you supply the heat, so this will be the position, location, means now the temperature is very close to the 100. It can be a 98-97 degrees Celsius now. And what happened at this point, what will be the vapor and liquid compositions? So this will be the vapor composition, and this will be the liquid composition at that condition. So this is the basically the, now the vapor have the, about 30, less than 30, 28% vapor, means in the liquid, 28% A, and in the vapor it comes around 50% A is in the vapor phase. So this is the case at this temperature. And again you supply the heat, what happened, again you supply the heat, it will be reaches at this point, and at that point all the liquid will be vaporizes, and at this point the composition is 40%, but that is in the vapor phase. And if you again supply the heat, that it will reaches at this point, means the composition is same, only the difference is now the temperature is about 105 degrees Celsius, but it is a superheated vapor. So this is the phenomena when any material that is available in the subcooled is heated, then how the subcooled is converted into the superheated, what are the different steps and different the changes different changes taking place in the journey from subcooled liquid to superheated vapor. So till now, thank you very much. Up to this lecture, I will discuss the remaining portion in the next lecture. Thank you very much.